In this video, I will discuss the basics of ANOVA. First of all, the purpose of doing ANOVA is to compare 3 or more means, or to compare 3 or more groups. So our null hypothesis when doing ANOVA is null hypothesis all the means are equal versus the alternative that at least one mean is different. I always like to think of this as the Sesame Street alternative because when I was a kid there was a segment on the show where they broke the screen up and they always sang that song, "One of these things is not like the other." So if I think of it that way, I never forget how to do the alternative hypothesis. ANOVA stands for Analysis of Variance. It basically compares the variation within the samples to the variation between the samples. So if you look at these two sets of box plots here, in the ones on the left, they all have tall boxes, which shows that there's a lot of variation among individuals within each group. With this much variation among the individuals, it would not be surprising if another set of samples gave quite different sample means. So the observed differences could easily happen just due to chance. Now if we look at the boxes on the right side, they have the same centers as the ones on the left, but the boxes themselves are much shorter, meaning that there's much less variation among individuals in the same group. So it's unlikely that any sample from the first group would have a mean as small as a sample from the third group. So because the means are far apart and the variation within the group is small, then it's more indicative of a real difference among the means of the three populations. So ANOVA, what that's going to do is it's going to compare these. It's going to look at how much variation within the group and compare that to how different the different means are between the groups. There are two basic requirements for doing analysis of variance. First, the data for each group needs to be normally distributed. We can check this by doing a QQ plot of each sample. And if there's not any obvious departures from normality, we can feel pretty good about the normality assumption. The second condition is that the populations have to have the same variation. Now, obviously, we're not going to know what the population variance is, so our rule of thumb is to look at the sample variances, and if the largest sample variance is less than 4 times the smallest sample variance, then we're going to conclude that it's reasonable to assume that the population variances are the same. All right, so let's look at an example. Which color attracts beetles the best? An experiment was conducted to see what color attracts insects the best. 6 boards, each of 4 colors, were placed randomly in oat fields. The boards were covered with a sticky material, thus trapping insects that came in contact with the boards. The number of insects trapped on each board was recorded. So we were comparing 4 groups here, basically the 4 different colors of boards, blue, yellow, white, and green. And we want to know are the mean number of beetles for each of these trapped on each of these boards if they're different. So null hypothesis is that the mean for the blue board is equal to the mean for the yellow board is equal to the mean for the white board is equal to the mean for the green board, or in other words, all the means are equal, versus the alternative hypothesis that at least one of those means are different. One of those things is not like the other. The first thing we need to do is check our requirements. The first requirement is that all the populations are normally distributed. To check this, we're going to construct QQ plots of each sample to verify normality. The first thing you need to do is to get the data into the Excel toolbox. So here's what my data looks like. It's actually all stacked on top of each other. You can see all the measurements for blue are on top of the measurements for green, on top of the measurements for white, and on top of the measurements for yellow. And if I look at my toolbox, first I'm going to click on the ANOVA tab. You can see that in the toolbox they want each group in its own column. Before I actually paste the data in here, I'm just going to delete all the data that's currently in here so I don't end up with any leftovers. And now I'm going to go back and cut and paste one group at a time. So I'm going to start with blue. So I'm going to copy all the observations for blue, and I'm going to paste them in the first column. Then I'm going to go back and copy all the observations for green. Just hitting Control-C to copy and Control-V to paste. And I'm going to paste those in the second column. And I'm going to keep doing that until I have all my data in there. So next I have white. And finally, I'm going to have my yellow. Now that I have the data in there, I'm ready to go ahead and start analyzing the data. The toolbox makes this really easy. To check the requirements inside of the toolbox here, I'm going to scroll over, and if I keep scrolling, notice that it's going to go ahead and do the QQ plots for me. Now I do need to check the QQ plot for each group separately, but here inside the toolbox, if I click on that little yellow box at the top, I can toggle between the different groups that I have. So in this case, the different colors that I have. And I'm checking to see that the points mostly line up on a straight line. So here's my first group. You can see that they pretty closely follow a straight line. My second group, again, they look pretty good. My third group here, looking slightly curvy, but not too bad, still falling pretty close to the straight line. And my last one here, again, pretty close to the straight line. So we would say that we do meet the normality requirement. The second requirement is that all of the population variances are equal. And to do this, we're going to compare the largest and smallest sample variances. The largest variance should be no more than 4 times the smallest variance. If you look right here, it picks out the largest and the smallest variance for you, and then you just have to do the calculations to make sure that the largest is no more than 4 times the smallest variance. So here's my list of variances, one for each of the 4 different colors of boards. We can see that white was the smallest with 14.167 and yellow was the largest with 46.167. So we just need to verify that the largest is no more than 4 times the smallest. So I usually just set it up with this little inequality here. And if you plug in the numbers so that we have largest less than 4 times smallest. When you plug in the numbers, if it's a true statement after you work out the math, then you meet the requirement. In this case, 4 times 14.167 is 56.668, which is larger than 46.167, so we do meet the requirements in this case. To analyze the data, we come back here to the toolbox, and if we just scroll over to the right here, we can find all the information we need right here in this analysis of variance table. Let's take a closer look at this table. First off, we have our degrees of freedom. There's 2 types of degrees of freedom for analysis of variance. There's the between groups degrees of freedom and the within groups degrees of freedom. Sometimes these have slightly different names. Sometimes they're called numerator degrees of freedom and denominator degrees of freedom. Sometimes they're called groups degrees of freedom and error degrees of freedom, but it's all the same thing. So the top one is calculated by taking the number of groups minus 1, and the error or within groups degrees of freedom is calculated by taking the total number of observations minus the number of groups. The really important thing that we want to get from this table, or one of the 2 really important things, is the test statistic, which for analysis of variance is an F-test statistic, and the p-value, which is going to help us draw our conclusion in this test. So in this case, our F statistic, 42.839, and our p-value is essentially 0. Now, when analyzing data for an analysis of variance, a really good graph to compare the different groups is a side-by-side box plot comparison. And unfortunately, the toolbox doesn't automatically do that for us, but it's not too hard to produce a box plot inside of Excel. Let me show you how to do it. So I start here in my toolbox sheet, and I'm going to highlight all of the columns that contain my data. And I did go ahead and rename the tops of my columns to match up with my colors. You don't have to do that, but I like to do it to keep track of things. Next, I'm going to click on the Insert menu at the top, and I'm going to choose recommended charts. From this menu, I'm going to click on the tab that says all charts. And then if you look on this list, there's an option for box and whisker plot, and that's exactly what I want. So I am going to click on that plot and click on OK, and it puts it right here in the middle of the page for me. Now you can move this around to be wherever you want to. So I'm going to go ahead and move it over here to a blank spot on my page. Now these box colors don't match up with the colors of my boards. So if I wanted to get fancy and make them the same color, it's really easy to do that. In Excel, I can just double click on this box here and click on the little paint bucket. This one was the green one, so I'm just going to change that one to green, and I'll change this one to white, and I'll change, well, the other one already is yellow for me, so now I've got it matching up with the colors of the boards that were used in the Beetle experiment. I could tell by looking at this graph that the blue and the white are pretty similar to each other. So it seems like blue and white boards attracted the same number of beetles on average. You can see that green is quite a bit different from the blue and the white, a little bit higher, and yellow looks like it's different from everything else and that it attracted the most number of beetles. So after all this, what should we conclude? Well, recall that our null hypothesis was that all the means were equal, and the alternative was that at least one mean was different. Our p-value was essentially 0, and we all know that if p is low, HO must go. That means we're going to reject the null hypothesis, and we have sufficient evidence that at least one mean is different. And based on our box plots, we can pretty safely conclude that yellow has the highest amount of attraction for those beetles, green second most, and blue and white are the least and seem to be not very much different from each other. So what kind of action should you take? Well, be careful if you're wearing yellow next time you go into an oat field.